Hello, my name is Indiana Hoosier. Today I'm going to be presenting KI5. It is a receiving end of a cell phone. Because I'm in all three classes, I will be presenting everything. And when you look at this overview, you can see how the signal is going to be moving through the receiving end. It starts out with this antenna, which receives a signal from a cell tower. And after the signal gets received, it gets sent through this bandpass filter. This bandpass filter is needed because it filters out all the unwanted noise that we do not want. Then we have here a low noise amplifier. We need this because our signal is going to be very small when we first receive it, so we need to amplify that up so it's easier to work with. The next stage is it's sent through this mixer. This mixer is actually getting rid of the carrier frequency that it's on so that the frequency is based around 0, which is originally what it was when it's sent out, but because of this first mixer frequency, we need this one to counteract it. Now, the stage right here is an amplifier again because we need to amplify it up so that it's easier to work with as well. This low pass filter at the end is getting rid of all that extra high frequency noise that we do not want, because some of it will slip through right here, and with this amplification we need that in order to filter out the other stuff. Now, to increase the DC gain of an amplifier, we're going to expect all three of these things. We're going to increase the power consumption, decrease the bandwidth, and decrease the output swing. A good example of this is by VSET. If you increase VSET, you're going to be increasing the current, and by increasing the current due to Ohm's law is power with Ohm's law is power is equal to V times I, and if you're increasing I, you're increasing the power consumption. Now, with the output swing, pretty much every single amplifier there is, it's going to be cascoded, and the output swing, the top part of it is usually VDD minus 2V set. The bottom part of it is usually 2V set. So if you increase V set, you're actually decreasing the output swing, which isn't very good, but it's a necessary evil for most stuff. Now, the next thing we have here is a simple LC circuit. It's just an inductor and a capacitor put together. Using Kirchhoff laws and everything else, when we get VO over VI, we get 1 divided by S squared LC plus 1. Now, if you set this bottom part equal to 0, you'll see that there's a pole at 1 divided by the square root of LC. And that I'm saying is just right here. So when you draw a body plot, it'll be 0 for a while, and then it'll just drop off once it hits this point. Now, at this point, it's going to be negative 20 dBs per decade drop because there's only one pole. Now, if you can't ignore a resistor in there, then it's going to be the exact same process. The only difference is that there's going to be an RCS right here. And now, because of this R, in order to find the pole, you have to use the quadratic equation. And by doing the quadratic equation, you just plug it in there, and then you'll see you have two poles at two different points. Now, because the resistor is added, there's a few ways to compensate. The way that I compensated is I added another capacitor in series with this one, because if you look at this right here, this capacitor is on the denominator, and by increasing this up, it'll counteract this going up. I know there's a few C's up here, but they should counteract each other just because of the way that they're laid out. Now, if we have a perfect op-amp right here looking here, and we have a ZF on top, a ZI at the beginning, and if you do ZO over ZI equals negative ZF divided by ZI. Now these two impedances, they're going to be full of capacitors and resistors. And an easy way to find this is just doing Kirchhoff's laws, VI minus this voltage right here, and then this voltage minus this voltage. Both of those are going to be divided by their respective impedances, just doing the current going through there. Now this one is going to be relative to this one, so you know this is actually going to be a virtual ground when you do the calculations. Now, if you have an imperfect op-amp, you know that A is not going to equal to A anymore. A is, in this case, is A divided by 1 plus ST. Now, you know this is going to add a pole in there. Now, if you actually go through, for this top half, it's if you actually do have a perfect op-amp. But when you go through here, if you were to factor out these A's, it would be the same thing as what we had right here, the ZF divided by ZI, but then it would be multiplied by a certain multiple. Now, just plugging this into the A's, you'll get this function. And just like I said before, if you factor out all this A stuff over there, it'll still be ZF over ZI times a multiple of a bunch of different things. Now, here's a specific case of that. You have a RF right here and a capacitor, and then you have an R. Now, you know this RF and C are going to give you a pole. And just by plugging in C in parallel with RF for ZF and then RI for ZI, you plug them in there. For an ideal op amp, you're just going to get this function pretty easy. As you can see, you have one pole just right down here at the bottom. And for the non-ideal, you plug it in and you notice you're going to have another extra pole down there because this op amp has its own pole. And as you can see, it works just fine. This pole right here is the same as this pole right here, same exact spot. This pole right here is from the op amp, and the op amp's pole is not really affecting too much of the bandwidth, which is nice. Now here's another specific case. You have a capacitor there, and you have a resistor there, then a resistor and capacitor. Now add these two together, add these two in series, or in parallel, and plug them in for the different Z's like you did in the one before. And as you can see, there's also going to be a 0 now in this case, and there's going to be 2 poles for the ideal, and then 3 poles for the non-ideal, and 1 pole, or 1 0 for the non-ideal. And as you can see, the same thing it does. It has a 0 right here, which rises up. You hit 1 pole about right here, or you hit 1 pole about right here, get another pole about right there, which then gives you this nice bandpass filter. Same thing happens for the non-ideal case. Here's the extra pole from the op amp, so it's again not affecting it too much. For a while. Now the last thing I'm going to be talking about is the antenna. The antenna is actually this stacked on top of this to look like this right here. At these little points right here, and right there, they're actually connected by wire going up, and so it actually makes this loop. That way you can actually condense the antenna into a smaller area. If you add up all these lengths, it equals the correct wavelength that you need. There's 50 ohms for an input right here, and it's good to know that all the resistance throughout here, using fringing effects and everything else, it'll equal about 50 ohms. And because they're relative, there's not going to be any power reflection that's going to come back and disturb all this, which is really nice. And also the wavelengths meet up pretty nicely too. And here's all the relative sizes that we use to add up everything. And thank you for watching my presentation. Here's a little funny thing. I hope you enjoyed it. Ohms, which is exactly what you want because that is the best possible way for the ohms to be. And